In this example, we're going to look deeper into hypothesis testing. Go ahead and read through the example on this web page. The basics of what we're going to be doing is we're going to look at how to make inference about heart rates in healthy young adults. And the way that we're going to do that is we're going to take a subset of the Framingham cohort that looks like a population of, quote, healthy young adults. We're going to test the hypothesis that the heart rate at follow-up at exam 2 would be lower than 80 beats per minute in this cohort, which is the resting heart rates for adults with average health. Now, when we do this, we are making somewhat strong assumptions that these Framingham participants are generalizable to a broader population of healthy young adults, and this assumption is necessary if we want to make inference about the population of healthy young adults. Now let's get started with hypothesis testing. Anytime you want to do a statistical hypothesis test, you need to go through a set of steps. The first step is choose a test. In this example, we're going to look at a one-sample t-test. Next, you would state your null and alternative hypothesis. Step 3, actually go ahead and do the test. Step 4 is you need to present your results. And by that I mean you should show your test statistic, p-value, and any other relevant information. In step 5, you're going to actually make the conclusion of rejecting the null, or you can fail to reject the null. Note that you would never, ever, ever say that you would accept the null hypothesis. And the final step, step 6, is to make a conclusion about your data. So in this example, if I rejected the null hypothesis, I might be able to say that from our data, we have evidence that the heart rates are lower in healthy young adults. That would be the conclusion that I would make about my data. Now let's get started with hypothesis testing. Go ahead and open up Stata on your computer, and in this module, we're actually going to use a different data set. That data set is on this web page. It's called healthyyoungadults.dta. Go ahead and open up that data set as well. Recall that in this example, I'm interested in testing whether the mean heart rate in healthy young adults is equal to 80, and that's 80 beats per minute, versus the alternative hypothesis that mu is not equal to 80. Now to test this hypothesis, I'm using a one-sample t-test, and the reason that I'm doing that is that I don't know the standard deviation of heart rates in my population of interest. So when the standard deviation is unknown, I'm going to use a one-sample t-test. I'm also making another big assumption here, namely that my data is normally distributed. So I need to assume that the heart rates in healthy young adults are normally distributed. All right, once I make that a normality assumption, I can go ahead and do my t-test. However, we should just go ahead and check, first of all, that normality seems to be a reasonable assumption. And to do that, let's make a histogram. So I'm going to make a histogram of heart rate at exam 2. Now looking at this histogram, if I look where most of the data is between 50 and 100 beats per minute, you see that normality might be reasonable within that range. However, this outlier out here, it makes it very difficult to even assess the normality assumption because this is such an extreme outlier. So that's the first thing you should notice. Now let's make a histogram when we exclude this outlier and see if, omitting that one observation, does normality look okay? So I'm going to make a histogram for the observations where heart rate is less than 200. There's only one observation that exceeds this. And now when I look at this distribution, we see that nothing weird appears to be going on. Drawing an exact normal curve over this guy is going to be difficult. It doesn't look exactly normally distributed. However, we're dealing with a small sample size, so usually when you're conducting a t-test, the t-test will perform okay as long as you don't see anything really weird going on, as long as you could plausibly think here, yeah, this data could be normally distributed. It looks pretty symmetric. Things look like they're okay. We have a small sample size. It's difficult to say anything concretely. Okay, so let's say that as the statistician, we're willing to make that normality assumption, and we've decided we're going to do a one-sample t-test using the hypotheses that we saw before at the alpha equals 0.05 level. So remember, anytime we've made a decision about a hypothesis test, we always go through the steps. 1, we say we're doing a 1 sample t-test. 2, we state the null and alternative. We saw those before. I'm not going to repeat them for sake of time. And then step 3, what do? We do the test. Now in Stata, there's many different hypothesis tests that one can do. So to examine the different t-tests you can do in Stata, type db t-test. And you see that all these options pop up. The first one is a 1 sample mean comparison test. That's the test that we want to do. The rest of them are all 2 group or 2 sample tests, which we'll look at in next week's tutorials. Now down here we also have these t-test I dialogues, and you have this 1 sample mean comparison test calculator. We'll see how this option works as well, but for now, let's focus on the 1 sample mean comparison test. So click on that. The variable name that we're interested in is heart rate 2. The hypothesized mean is 80, and remember the confidence level is 95. And let's hit submit, and you now see in Stata what the results for a t-test look like. You get many important numbers from the output of the t-test command. We have the number of observations, the mean in the sample, the standard deviation of the sample. You also get the standard error of the mean, and you get a 95% confidence interval for the mean. Now for the hypothesis test, many of the important quantities are down here. You have your t-statistic and the number of degrees of freedom. And then down here you have p-values for a one-sided test, the other one-sided test, and then the guy that we're interested in, the p-value for the two-sided test is here in the middle for the alternative that the mean is not equal to 80, and you can see that my p-value is then 0.2237. Now, anytime you're presenting the results of a hypothesis test formally, you would want to give several different pieces of information here. First, you would want to say my test statistic is negative 1.22. Actually, negative 1.23. My degrees of freedom, there's 60. So what I would say is, in this hypothesis test, I would say my test statistic is negative 1.23, and this test statistic, we'll call it T. Under the null hypothesis, this test statistic follows a t-distribution with 60 degrees of freedom. Given that null distribution, we can then say that my p-value is 0.224. So anytime you're presenting a test statistic, you can see this logical progression from here's my test statistic, here's the distribution of the test statistic under the null hypothesis, which leads me to my p-value. Given that my p-value is 0.2237, in step 5, I know that since p is greater than 0.05, I'm going to fail to reject. So in step 5, I fail to reject my null hypothesis. In step 6, I would say something that we do not have any evidence in our data to suggest that the heart rate is different from 80 in healthy young adults at follow-up. So we don't see any evidence for the alternative hypothesis in our data set. Now let's briefly look at if we were to do this test instead of using t-test, if we did t-test I instead. So to find the t-test commands in the drop-down menu, you go Statistics, Summaries, Tables, and Tests, Classical Tests of Hypotheses, and then you have this 1 sample mean comparison test. That's what we just did. We also have the 1 sample mean comparison calculator. Click on that guy. My sample size is 61, and I can plug in my sample mean of 76.56. My sample standard deviation, which is also provided right below. The hypothesized mean, recall, is 80. I want the 95% confidence level, hit submit, and I get results that are basically identical to the results from the t-test command. This is the t-test I command. The only subtle differences you'll see between the two are due to rounding error in the mean and the standard deviation that I typed in here. So t-test I gives the exact same results as t-test. If you're working within Stata, if you have your data read in, you would never really actually use t-test I. Typically, you're just going to use t-test and, going back up here to this notation, you would just feed in the variable that you're interested in. That's what's going to be more convenient in practice. But if you don't have data read in and you just know the mean and the sample standard deviation, you can still do that test within Stata using the t-test I command. Okay, so that's the logistics of how one would do a t-test in Stata. let's go back to thinking about this test that we just did. I saw that I ended up with a p-value that was not statistically significant, and I ended up with a very large sample standard deviation here. As the diligent statistician that I am, I would think to myself, I'm probably not treating these data correctly because I have this very extreme outlier. Now let's look at the outlier in our data set. You can do that by typing list if heart rate is greater than 200. And you'll see I get all this information for the healthy young adult in our population that had a heart rate greater than 200. And looking at this study participant, if we look through all of her data, she looks really healthy. She has no red flags. She never really deviates from her healthy status throughout the study period. She never has any major cardiovascular events, but she has this ridiculously high heart rate at exam 2. Now, the Framingham dataset is a very well-managed dataset, and it's really hard to imagine that typographical errors actually exist in this dataset. However, unless this participant went and did a bunch of wind sprints or something directly before her exam, it's really difficult to imagine why her heart rate is so high. So as the statistician, this really puts you in a pickle. You have to think to yourself, is this a typographical error? Did my data management people read in the data correctly? What's going on here that could create this observation? So anytime you have an outlier, you need to think really critically about how this outlier popped up in your population. Now let's go ahead and briefly repeat the t-test that we did before, but let's exclude the outlier from our analysis. To exclude an observation, you would need to go to the By If In tab. We would restrict the observations if heart rate 2 is actually less than 200. We only want to include those participants who have heart rate 2 less than 200. So we repeated the t-test. Now if I look at the results from the previous t-test, it might be interesting to juxtapose these two results. Let's look at them. So when I include my outlier, the standard deviation of the population of healthy young adults is 21.9. When I exclude it, it's 11.4. It's almost halved. So you see that the means are a little bit close together. You see you definitely have a lower mean in this situation because you have excluded that extreme outlier. But then the standard deviation of the mean you see is just so much lower once we exclude the outlier. And now our p-value has actually decreased from 0.2237, and now it's all the way down to 0.0002. So if I were doing my test, I would present all of this information. I would say p is less than 0.05. Therefore, I reject my null. And I would say that when I exclude my outlier, I actually see pretty strong evidence that the mean heart rate in healthy young adults is less than 80. So this brings us to the conundrum of, as a statistician, which results should you present? Should you present these results without the outlier that seem to support our hypothesis versus the honest results where I don't delete any observations, I just analyze my sample as it is, and I find, results that are not statistically significant. Also, when I don't exclude my outlier, it's likely that the assumptions of the t-test are not met. We have that very extreme outlier, which brings the normality assumption into question. So, as a statistician, what do you do with an outlier? This is always a really tough decision in an analysis. It's very, very bad practice to throw out the outlier and pretend like it never existed. You really can't just throw out data unless you have very strong evidence that it's a typographical error. But in this case, leaving the outlier in, we don't meet the assumptions required for the t-test, and the results aren't representative of the entire sample if you decide to do the t-test anyways, because that outlier is changing the standard deviation and the mean so much. The problem here is that the t-test really isn't robust to outliers. It would be very nice if we did have a statistical test that was robust to outliers, similar to, remember how the median is more robust than the mean to outliers. Fortunately, some very clever statisticians did make up such a test, and we call these non-parametric statistical tests. And we'll learn about these tests in the upcoming weeks that are going to be robust to our outlier, and hopefully we can revisit this example in the upcoming weeks, and we can show you how there is a happy compromise here where we don't have to throw out any data, but we obtain a statistical test that's robust to any outliers.